Okay. R minus 2m is, again, delta. Right. Actually, let me erase this. I'm doing the same work twice, because after all, you recall that we figured out how to express delta in terms of c. We calculated that formula by setting this term equal to dc squared. So having already done that, there's no point in doing the calculation a second time. This is merely dc squared plus r squared d omega 2. All right, and now to write this, what is delta over 2m in terms of c? Okay. Well, it looks to me like delta, 2m delta is equal to c squared over 4. And therefore, delta over 2m is equal to c squared over 16m squared. Right. So when all is said and done, we have now written the metric as minus c squared over 16m squared dt squared plus dc squared plus r squared d omega 2. Okay, so almost done. If you look at this, that's, plus higher order terms in delta. So indeed, we have almost matched this form of the metric. Okay? The only remaining step, if you look at that metric, indeed the r squared d omega 2 term is there. The dc squared term is there. This one is almost right. The only difference is that we see that we should define theta to be t divided by 4m. Okay? If I did that, that would clean up this factor here, and I would find that the metric for the black hole is indeed minus c squared d theta squared plus d c squared plus r squared d omega 2 plus higher order terms. Whew. Okay. Good. So, regardless of whether you followed every step of the algebra with me, we've now arrived at our stated goal. We've taken the commonly expressed form of the black hole solution, the Schwarzschild solution, and we have written it in a way that we can see that near the horizon, it is exactly like this acceleration horizon we saw before, with the addition of this extra 2 sphere. It's just the same. So now if we have any questions about black hole physics, at least about what's going on near the horizon, we can answer them basically by looking at this picture and just reading off the answer. Good? Good. Okay. Let's see. If it's a question about Hawking effects near the horizon, then indeed, at least in standard quantum field theory and curved space-time modulo things that no one understands yet, yes, you can work out the answers from within their space. And this is often a very useful perspective to take.
You have singularities at the horizon?
Excuse me?
Obviously, we have singularities at the horizon.
A good question, but I will let you answer that for yourself. If you look at this picture, do you see a singularity? This is Minkowski space. Okay. So, from what I've said so far, if we're worried about what happens at the horizon or close to it, the answer should follow from Minkowski space. what we see is the horizon is completely non-singular. It's just a fine place. What it was a place where if we insisted on using this accelerated coordinate system, there's a problem with the coordinate system. As we mentioned, the coordinate system covers only this wedge. To cover the future wedge, you have to use a different coordinate system. Okay? Which one can also do in the black hole case. One can consider the so far, we've been working outside the horizon. Okay? We worked at, you see, somewhere important here. I took a square root of delta, and I therefore assumed that delta was positive. Okay? So I've worked outside the horizon. So you might ask, well, what happens if I do the same trick inside the horizon? Okay? It can be done. To do this inside the horizon, one merely does the same thing, starting here, keeping track of all the signs properly, but doing it for r less than 2m. Okay? If one does that, what one finds is this metric here, plus r squared d omega 2, where you may recall this is the metric that we found. Well, we didn't go through the calculations, but this is the metric that I mentioned you would find up here in my Minkowski space. Okay? So this is a calculation that I will save for your workshop period or your homework period. But you can do the same calculation I did for, again, delta just slightly negative. And you find that this Schwarzschild solution now matches on to this coordinate system associated with observers up here. Okay? So what happens when you cross the horizon is just what happens when you cross the horizon here in Minkowski space. You go just from this region to this region, like so. Well, so, okay, if you're inside the black hole, that's like being up here. Okay? There are many observers up here. Some of them are following inertial trajectories. Some of them are accelerating. Some of them are accelerating the other way. Okay? In the same way, inside a black hole, there are many observers. Okay? And which one you do is sort of up to you. The thing you can read off this diagram is if you choose one of these observers, say the one who falls freely and turns their rocket off, okay, and you ask what happens if they look at someone who stays outside the horizon, okay, you can use this diagram to, for example, trace light rays that travel between these observers. Okay, and you can worry about the associated time dilation effects and so forth. What you see, of course, is it's asymmetric. The observer who falls in can receive signals from the one who stays outside, but any signals from the observer inside, of course, remain inside the horizon. Okay. Jeff?
How close is this? So the metric, at least with the, talking about the sphere part, that looks pretty much like none.
Yeah.
How close is the?
It is none.
It is none. So how close is the So what happens there at the singularity down there?
Where?
So
there's no singularity in this
all
picture.
of those string theory papers that have come out recently.
Okay. So there's this thing called the Milne universe, which is given by taking a quotient of this spacetime. Okay, it makes identifications. Those identifications, if you make those identifications, which you would not do for a black hole, but you might do for a cosmological model, that creates a singularity here. Right. So if you make those identifications, you have a singularity.
I just asked because Horowitz and Pochon's paper recently, and they said that the singularity in the Milne universe is no better, no worse than Schwarzschild singularity.
That's the result of their paper, though, right?
Yeah.
Including gravitational back reaction and so forth. Yes.
So what does that mean? How bad is the singularity at
Well, so I haven't mentioned the Schwarzschild singularity yet, so let me do that since it's been asked about. Okay. So far I've done things near the horizon, and everything's fine. The space-time is not singular or, terribly strange in any way. It just has these properties we discussed. On the other hand, you see that there are also problems with this metric at r equals 0, not just r equals 2m. At r equals 0, there's a divergence here. Okay? And it turns out that at r equals 0, nothing like what I've said is true. At r equals 0, that's now far from the horizon. It's very different. Okay? Please.
What happens to that second term when y1 minus 2 of r is equal to 0?
That one?
Yes.
What happens to that term where?
Yeah.
At the horizon?
No, you made it equal to 0 first. That vanishes.
This one?
Well, we had it somewhere.
Yes, this term vanishes at the horizon. Yes. This term diverges at the horizon. However, what you've seen is that, in a certain sense, that's a fake concern, because if I change coordinates, that problem goes away. Okay. So what that means is that this coordinate system is a very bad choice at the horizon. It's merely a problem with the coordinates, not a problem with the space-time itself. Okay. Yeah?
I don't know what determines the fact whether you run asymptotically to the horizon or whether you cross it over the horizon. Because you just do that line straight. But how do you not know that it's just going to run asymptotically to the horizon or it's going to cross over?
So this is a question of what the dynamics are. Okay? Imagine this is an observer with a rocket ship. Okay? Then if the observer turns their rockets off and follows some inertial trajectory, you can see they will always cross the horizon, because inertial trajectories look like either this, or like this, or perhaps like that, but always moving at less than the speed of light, so it will cross the horizon. If, however, the observer turns on her rocket engine and chooses to use that thrust to accelerate away, and if she calibrates it properly, she can manage to be asymptotic to the horizon. Okay. Actually, if you're really going to be asymptotic, that probably requires an infinite amount of fuel, okay, which is tough, but you get the point. Okay. All right. So just a word or two about the singularity. The singularity is something that lies at r equals 0. R equals 0. So let's put this here. Singularity all right. And again, you can see from this metric that it looks like r equals 0 is going to be a funny place. Now, of course, that can be deceptive because it also looked like r equals 2m might be kind of funny, and it wasn't too bad in the end. But r equals 0 is a place to look out for. So let's think a little bit about what r equals 0 is. Let's also think about where it is on this diagram. Okay. So let me draw this again down here. I like yellow for my light rays. So there's the horizon. Here are these uniformly accelerating observers outside. And if we're working inside, there are these interesting lines. Now, I ask you, where on this diagram is r equals 0? Well, clearly it's inside the horizon, because inside the horizon is r less than 2m. So this is r less than 2m. Okay? So let's see. So we had all these nifty lines on here. So which of these lines represent r equals 0? Is r equals 0 a line like this, or a line like this? Well, let's see. What we saw, let's see.